friends, yeah, just a few moments of bringing ourselves out of our heads for a moment. Use this as a transition into some math. But first, no math. So just sitting up, taking note of your body and what are you sensing right now? Where is your awareness taking you? Slowly transitioning to an awareness of your breath. While you do this, letting your shoulders relax a little bit. Letting your jaw release. Just taking note of the natural rhythm of your breath. Not trying to control it, simply as an observer. Watch what is happening. How granular can you get your attention as you study your breath as though your life depended on it, but in the most relaxed way possible. Just gently returning.
Sorry.
It's all good. We started early. Having noises happen doesn't bother us anyway. It's just more interesting texture to the things appearing in our awareness. Got some news for you. Some of if the top one's news, Godspeed. You've got some work to do. So there's a web work due tomorrow night. I'll take questions if there's any. There's a new web work that will be up tomorrow on stuff that we covered today. And Diego brought my attention back to the weather forecast for Wednesday. So if the weather's bad, I will send out an email and we will just meet via Zoom. We won't cancel class except for Friday, when class is already canceled. So we do not meet on Friday. And first math club meeting of the year. It may not sound like a very cool thing to do. It's classically the thing that might be made fun of in a movie, going to math club. But it's a pretty relaxed place, especially if you're a person who feels awkward about socializing. Come to the place where everyone feels awkward. Come to be with the mathematicians. where no one really wants to talk, yet we do anyway. Tonight's game night, by the way. So they play some kind of logic game. I forget what it is. That doesn't sound very good either. It's like a mystery game where you try to figure out who's a spy or something like that. It's pretty fun. And you can connect, maybe meet some new people, and tonight you don't have to learn any math. So it's a good time to do it. See, nothing else over there. Questions on the web work that is currently open? Anything you'd like to discuss? Joey, yeah.
I had a problem or two I was stuck on, and we can go through it.
Sure.
Pull it up.
Just let me know when you got it there. I'll need you to read it to me, that's all.
Yeah.
I've been telling people about your Ethereum mine, but don't worry, I'm not going to tell anybody who would shut down your Ethereum mine.
Yeah, don't do that.
No, I won't, man.
It was question 11, I think.
Okay, so number 11, could you read that to me, please?
Find the equation of the tangent line to the graph of y of x equals 4 parentheses x minus 1 over x parentheses squared at x equals 2.
Love it. Cool. Find the equation of the tangent line. Now, let's do a different one. Let's do, I don't want this exponent to get too crazy here. I'll do this problem, Joey. Should be good. So we want to find the equation of a tangent line. Step 1 is get the point. X naught, Y naught. So I've given X naught, that's this is be your X naught here. You have to go to the equation and plug that in. So here, Y naught is going to equal 3 times 3 minus 1/3 to the 4th, and instantly regretting the numbers I've created for myself. So let's see, what is that? 8/3 to the 4th. So that's 8 to the 4th over 3 to the 4th times 3. Oh shit, well, can I do this? I think I can do this maybe, because this is 2 to the 12th, and I think that's 1,092? Somebody check me on that. What is 8 to the 4th? Is it 1,092?
4,096.
4,096. Hey, there was a 0 in there, so I'll take that, and 4 digits, so that's pretty good. So 4,096 over 27, whatever. That's the point. Your point will be much less painful. 2, get the slope, which is going to equal the derivative at x naught. So here, I want to take the derivative of that thing. Couple ways you could do it. You could FOIL it out, and then group, and then use the power rule. But what I'm going to do here to find my derivative is use the chain rule. And check this out, Joey. I am going to rewrite 1 over x in a form that's ready for the power rule. So I would do the same here, change that to x to the negative first. So now chain rule says I got 3, bring the 4 out in front, x minus x to the negative 1 to the 3rd, decrease the exponent by 1, times the derivative of the inside. And so that's going to be 12. This just copies over. Derivative of this, derivative of x is 1. Keep the parentheses here too, otherwise things could become incorrect down the line. And then this is going to be minus. Power rule on this bring the negative one in front, goes to x to the negative second. Let me stop there. Does that make sense?
Yeah.
Any questions at all on it?
Not really.
No? Okay, awesome. So I'm going to evaluate that at 3. So at x equals 3, this becomes 12 times 3 minus a third cubed, that's 1 over 3 right there. Then this becomes 1 plus 1 over 3 squared. It's getting pretty gross, Joey, but I'm going to get some number. Yes. We'll call it M. Just crank that out, get that number. And then my final answer is going to be using point slope form. Plug in what I know. So it's going to be that M that I was too lazy to find. I've got 3 plus my god awful 4096 over 27. Sound good? Cool. You said you had another one?
I think it was number 2.
Okay.
It was maybe your advantage to simplify first with f of x equals parentheses x to the 6th, and then minus 3 square root with the what's like on top of square root x parentheses well
Third root.
You said something there that I didn't.
Third root.
Third root, got it. Okay, cube root, got it. Like that?
yeah. There's you add another 3.
I think it's just the cube root, not
Yeah,
3
just the
times the
cube
cube
root.
root.
Oh, okay, gotcha, gotcha. Like that, okay.
And then it's n parentheses and then 6x.
So, like this?
Yeah.
Okay. Yeah, so what did they ask you to do, find the derivative?
Yeah.
So yeah, I would recommend, I mean, you could just go straight up product rule on this. That would be fine, no problem with that. Derivative of this times that left alone, plus vice versa. So I could do that, blah, blah, blah. But I do think simplifying is going to be easier. So if we simplify, I'm going to have 6x times x to the 6th, that's 6x to the 7th. I'm adding the exponents. Noticing that this is x to the 1/3. Really important to note that. For no matter how I approach this, minus 6 times, so look, I've got 6x times x to the 1/3. I add those exponents, so it's 6x to the 4/3. And then at this point is power rule. Does that make sense?
Yeah.
Yeah, it's pretty straightforward. Any other questions on that homework? Okay, take your word for it. Let me hand out a couple of things. And back here, we're going to start something. We are going to learn how to take a new kind of derivative, one of my favorites. I always look forward to this day. I usually look forward to most of the days in this class. There's always something new and exciting to show you, to work on together. First, we need to pay some dues. So let's talk about inverse functions. And I should probably talk about functions first, because there are some folks in here who do not understand functions. If you repeatedly are having issues with functions, especially when you're doing derivatives and using that definition, please, 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 at some point you're going to have to help yourself. You have to. If you don't understand functions, and you got back corrections or something, and there was a number of folks who I wrote on there, you need to go review Alex about functions. you have to do that. I can't do that for you. And if you don't do it now, things are gonna get snowballed, and it'll just get worse. Happy to help you, but you have to do some groundwork first. So let's say I've got a function, f, and we might not have seen this notation before. So what this means is f is a function that immediately writing this means this. And it takes inputs from set A. And it spits outputs into set B. Those are not very technical words. This is called the domain. It's all the valid values. This is probably less well known. This is called the codomain. May or may not be the same as the range. So you've heard of the range of a function. The range is all possible things hit in that set B. Sometimes B is larger than the range. It's a subtlety that you don't really have to worry about, but it's the truth. So for example, take f of x equals natural log of x. Sketch out a graph of that function. Sometimes getting a graph can help us understand all sorts of things. So natural log looks like that. And you can see that it's got a domain that doesn't include any of this. You can't take the natural log of a negative. Can't take the natural log of 0, because that's an asymptote. So here, the domain of f is just the positive reals. So from 0 to infinity. Everything from here on up. Those are all the valid values. But notice, it can actually take on any value. It uses every portion of the y-axis. You draw a horizontal line somewhere, that horizontal line hits the graph somewhere. So the range, and this is all values that the function can take on, is the entire real number collection. It can hit anything. Let's contrast that really quick to another function. What if I have g of x equals e to the x? This is actually going to come into play today, and that's why I'm picking these guys. So here, e to the x looks like this. That goes through 1. So the domain, it looks like all values are good, is negative infinity to infinity. Everything, I can put any number I want in there and it's all good. But the range, look here, it only takes on positive values, so none of this. The range is everything from 0 to infinity. It's only using y values from 0 to infinity. Horizontal lines up here all intersect the graph, no matter how close down here they are. Notice how these two have reversed roles. That the domain here is the range there and vice versa. Yeah, oh Kelly, yeah.
Isn't there a vertical asymptote at 0 on the graph e to the x?
There is not.
Or horizontal, I mean.
There is a horizontal, yes, absolutely.
So then couldn't it never actually be 0 because it just gets closer and closer to it?
I 100% agree with you, yes. But that's why I put an open circle here. Yeah, so great, that's a great question. So this would have been completely incorrect because I can't achieve 0.
Okay.
I like that. I like that you're thinking about that. So this, if you're not familiar with this notation, this means don't include the endpoints. If you use these guys, these mean include. Awesome question. Any other questions? That was thank you. All right, so I don't want to get too much into the details of this because I don't think it's super helpful to talk about functions in the abstract, at least for this class. But let's suppose there is another function, g. also, if you don't understand functions and you just like for some reason resist Alex, let me know and I'll put a bunch of videos up by Patrick JMT to help you understand functions. Happy to do that. So suppose there's another function g that goes like this. It actually goes backwards. It goes from B to A. So this f goes from inputs here, outputs here, and g's doing the reverse. It's taking the output space from f, spitting out into the input space from f. So you could draw a picture like this. If this is set A, this is set B, f goes like this, g goes like this. It almost looks like we could make a full circle there if we used them both. We could ride f from here to there and then g back. And that's pretty much what I want to say here. So suppose there's another function, g, such that, or so that, if I take f of some element x, so I input this x here, and I get out a point over here, f of x. So the x is input to f, spits out a value, and then I apply g to that. So now, over here, I take this point and plug it into g, and I end up back over here. If that takes me back to the same place, if running through here and then taking that output and running it through g gets me back to the same place I started, I've made a full circuit, that's a good thing. But we also want to make sure it goes the other way. So if I take first g of something, so if I take a y here, and I take it and run it through g, so there's g of y right there, and then I apply f to that, I want to land back up at y. So in other words, f of g of y equals y. So this is composition, and this is good for all x in A, and this is good for all y in B. If this happens, f and g are inverses of each other. They undo each other. You apply f, then apply g, you get back the same thing. Apply g, then apply f, you're back to the start. Then f and g are inverses of each other. And in fact, we can write this. And we write g of x is actually f inverse of x. So check out this notation. It's very specialized. When you see a negative one like that, this means inverse. Not 1 over, nothing like that. It's just notation indicating an inverse. So that's all I really wanted to talk about. You can call this thing here, this is called F inverse. So let's look at some examples. I don't even need to draw any more of. I've started with some examples of this right over here. These two functions are inverses of each other. So let's go here. Examples. The inverse of e to the x is natural log of x. Because if I take e, first I take the natural log of something. I take an x, I take its natural log. And then I apply e to that. So in other words, e to the natural log of x. Look, check this out. Make sure you understand that this means first do the log, then do this. That's equal to x if x is a positive number to begin with, because that's the domain of natural log. It's got to be positive to begin with. And if I first take an x and then run that through e to the x, and then do the natural log of that, I also get x. that's good for any x. So they are inverse functions of each other. And you really should keep, this thing right here is super helpful. This relationship, it's gonna actually help us today in doing something. So I don't want to say too much more about inverses. We'll say it as we need to as things go along. This is enough to get us rolling for today. So, if, I won't even look at anybody, you just tell me, if you are like freaked out by natural log, if you look at that and go, I don't have a fucking clue what that means, send me an email. Send me an email, sorry about that, and I will send you videos to help you orient yourself. You absolutely have to understand natural log for the rest of the semester, as well as our good old buddy here. So, let me know, and I will hook you up. So, okay, we want a derivative for natural log. It's like the one function we haven't really talked about. There's a whole slew of them, but it's the most obvious. We want the formula. To get the formula, we're going to use this relationship here and the chain rule. To get the formula, use the relation. So I'm writing out what I just said. E to the natural log of x equals x. And take the derivative of each side. And take d dx of each side. Now one side's super easy. I hope we can all do the right side, because that's just one. If two things are equal, then their derivatives are equal. So this thing, yay, that's one. The left side, we need our formula. To take the derivative of e to something, you copy it down times the derivative of the exponent. You've used that a couple of times, so let's do it over here. This is going to be e to the natural log of x, I copy it, times the derivative of the exponent, which is just natural log of x. I stop so you can process. Wow, it smells good. This is like came out from this little like hood. The room smells nice. Compared to the dang stinky pit my nose lives in all day long. So, anything that I can simplify here? Here's what I want. Yay! Anything can be simplified here. Claire?
E to the natural log of x is x.
Beautiful. So this is just x, because they're inverses of each other. So this, thank you. So this is just x times derivative of natural log of x equals 1. Holy shit, look at this. There's your formula for natural log. The derivative of the natural log of x is 1 over x. And this is provided x, the side condition that you'll probably forget about and be fine doing so is that x has to be positive. Because otherwise the natural log doesn't work. We can extend this formula just a little bit. So let me show you an extended version. You can say the natural log of the absolute value of x is actually equal to 1 over x, provided x is not 0. So this is the one you'll probably use most. Sometimes that one will need to be known. Just remember that absolute values don't matter. that's the great thing. So let's get a chain rule version of this. So those are good basic versions. Here's the chain rule version. If I take the derivative of the natural log of something, so now that doesn't have to be x, that could be, good Lord, anything we want. To take this derivative, do the derivative of the outside, keeping the inside the same. Well, what would that mean here? That would mean I'm going to take 1 over the stuff that's here, times the derivative of the stuff inside. So that actually just ends up looking like this. That's your formula. That one will get, if you just know this one, you'll be able to do everything. So let's do some examples now. If I take the derivative of the natural log of sine of x, what a crazy expression. What's in the box? The sine of x. So check this out. This is a beautiful, beautiful rhythm. It's the derivative of sine over sine. Derivative of sine is cosine. The bottom. Done. So I could, like if I want to get fancy, what could I call this? Yeah, cotangent of x, if I wanted to get fancy. Derivative of the natural log sine is cotangent. Who'd have thought? No, probably nobody, because nobody's worrying about it on their own time. Fair enough. Good for you, actually. There's better things to worry about on your own time. Certainly better math problems to worry about. Let's do some practice. So I've got a whole slew of things. Let's start out chill. Please find the following derivatives. That one. Next. And let's actually shake this up a little bit. Put all sorts of nice rules in. Let's do a few.
Is there like a PEMDAS when it comes to this stuff? Because it seems like in these situations you're like, oh, do the product rule first and then the chain rule. Is there like an order of operations? Because I seen on the last one where one was speaking on like these, I don't know if I should chain rule it first or simplify or put a product rule or function rule, especially when there's like multiple rules in play. Is there like a standard?
There is, but it's harder to write out than PEMDAS because it really results in an understanding of composition. So it's being able to, and sometimes there's multiple. Well, like for example, Alex, let's say I asked you to find, and I think this is one we even did something like this in class. So when I look at this, I see that there's a product in top, but the whole thing is a quotient. But the outermost thing, the last thing that was done was the quotient, right? Along the way, if I was creating this, I would have to do the product rule, but then after that, I would do that as part of the quotient. So it's kind of like working backwards through the composition. So here I would realize quotient rule first, and in the process of that, I will need a product rule. So I think it's more a matter of experience, and I wouldn't try to write out that's a great question.
Yeah, I was just curious because I've been working through it and I'm like,
Yeah. So I guess the rule would be outermost function in the composition, working your way. Yeah.
and then more practice.
Yeah, it is. It's really just practice and getting used to seeing the things over and over again. I'll make sure you have plenty of practice.
That we'll talk after class.
All right. And then my favorite. So that one's off, but the other's beautiful. Yeah. Yes. That's right, that's right. And we were gonna talk about them today, but not quite yet. Bless you. That's true. Did you have a question, Leanne? Yeah. Looks lovely. Good, good. Sure, you put a stumper up there for you. Way too fast.
For the second one, is that equation equivalent to the derivative of the natural log of x cubed?
That is not,
It's not?
no.
That's weird.
There is no log property like that.
Is it equivalent to the natural log of x to the x squared?
It's that, which sounds worse. So Alex, so if you have something times natural log of something else, you can bring that in as an exponent. That's about it. If you have sum of logs, it's the log of the product. And alas, nothing like that here.
Want to look at something over here real quick?
What's that?
Want to look at this real quick? I'm not just want to show you that. That just looks that up for an idea and it says that.
Yeah, that's just wrong.
And what's wrong?
Well, that's right. Why don't you just stop looking stuff up?
Okay.
Just
I was
think.
just curious because I didn't
Yeah.
know how to approach that, so.
Yeah, whoever, I would not use that website.
That's Google.
That's bullshit. Yeah, I'm curious what that website is, because that is like, that's pretty bad.
That's pretty bad.
That's pretty bad.
Um,
Well, let's type this stuff out. You know, and there's always extra credit, or partial credit, by just simply writing out the rule, showing that you know it. This, wait, let me finish this up. Second one is a product rule. This one, hopefully you've got a little table that you're constantly referencing. If not, you really need to have a little derivative table of every derivative rule that we talked about, so you can reference that, and then you would know derivative of tangent is secant squared. There's nothing too fancy going on. Just tweaking, just getting a slightly new move in our calculus. Can't really do much with that. That's just what it is. And then I do love this. That's the derivative of the inside over the inside. And that can be confusing. But look at that law, look at that top rule. Lay that over your problem. What comes through the box? This does. This falls through the box when I lay that rule on, so I know exactly how to do this. I'm not even thinking to do this. I'm just a robot doing what I'm told. So this top is 1 over x over log x. That's great, but this is prettier. So next web work is going to be log heaven. Heard of hog heaven? We're going to be in log heaven. I don't know where that hog heaven thing came from. just stopped saying things. I don't know where they came from. Got a whole bunch of those in my head. Any questions on these terms? This log. If you can do these, you've mastered the logarithm derivatives. And we have one last collection of formulas to talk about. So today's all about inverses. I want to talk about inverse trig functions. Speaking of things people don't understand, these guys right here. This is like, even the most on top of it calc students occasionally will misconstrue these rules or misuse them, or maybe don't even remember them. I'm going to derive one, and then I'm just going to give you the rest, because you're not going to want to. Actually, if you like math, you might want to do the rest of the derivations on your own. But let's actually talk about what they are first. So, here, let me start off this way. Let's start with sine. So just think about sine of x. You should be fairly decent at making a sine sketch at this point. Not my best, but gets the point across. That's pretty bad. It's pretty distorted axes, but hey. So when you're working with inverses, the function itself works like this. You take an input and you get an output. So in and out. That's the natural flow of the function. The height of this graph is the output. What we want for an inverse is a rule that tells us, so let's see here. So for the inverse, wow. That's pretty bad. I'll probably kill myself on that. Instant karma. Throwing should. The inverse is, I want to take something that's originally part of the output and figure out from whence it came. So now notice this. If I say to you, hey, what inputs to sine give me that output right there? Well, here's one. So if I run this through, it gives me that output. But here's a problem. This one also gives me the same output. And over here, this one gives me the same output. And for any horizontal line you put here, it's going to intersect the graph infinitely many times. So let me write out what I'm saying is the problem. To get an inverse rule, we run into a problem. Given some y, and where would that y live? Between -1 and 1. Between -1, wow, and 1. Sometimes my spelling just starts to disintegrate. Given a y between -1 and 1, so in other words, this guy right here, there are infinitely many x such that sine of x equals y. That's not great for a nice rule. We want a rule that says, if you want to hit this output, here's the precise input to use. So we want only one of those. Because otherwise we don't have a function. A function can only give one output per input. If you have a function doing this, input, and then it does this, it gives you two different things, that's not a function. That's called a multifunction. And that's some fancy shit that we don't deal with. Not till 400 level math. So we need to restrict the graph, restrict the function to ensure that y equals sine of x has exactly one solution. That's what it means to go backwards. Here's the output. What input gives me that? So we want to have a rule for that. So here's what we do. We take the graph of sine and we cut it at pi over 2 and at negative pi over 2. So we cut the domain down to negative pi over 2 to pi over 2. Restrict that. And we do that because in this little window, look at it over here. In that window, all the possible output values are achieved. So like all the information we need is just in here. And this goes like this.
Wait, Dr. T, where it says negative pi over 2, shouldn't that be negative pi?
Yeah, I meant that to be, yes.
Okay.
Yeah.
Just making sure.
Sorry, yeah, I was thinking that too when I wrote that. I was like, so it's being noticed. So that refers to that line right there. Good call. So here's our sine graph. Now check this out. For any particular y value, now we have a unique x that solves y equals sine of x. So we don't have that problem that there's infinitely many possible inputs. So this is the function we are going to inverse. So find the inverse of this. And then this is from negative 1 to 1. And one of the properties of inverse functions is that to get the graph of the inverse, you just flip over the diagonal. So here's a graph of f and f inverse. They look like this. So if this is the graph of f, well, I don't want to, that's too wavy. So if this is the graph of f, here's y equals x. F inverse is just a flip over that diagonal. So it's going to look like something like that. So this would be the graph of f inverse if this is the graph of f. So the graph of inverse sine, and some of this stuff you're supposed to know. You might not, but you're supposed to, so I don't want to spend the whole hour reviewing that stuff. To get the graph of inverse sine, flip this graph over y equals x. And what you get is this. Notice that negative 1 to 1 becomes the inputs, and negative pi over 2 to pi over 2 becomes the output. So I've got this little box. And imagine that graph being flipped over, you get this. And so it's a weird graph because it just lives in that box and it achieves those points. But this is y equals inverse sine of x. Another fancy way to say that is arc sine, which I kind of like because people get confused about that and do weird shit to it. That's inverse sine. Let me quickly do cosine for you. This is to kind of speed it up. So cosine looks like this. To get a unique rule going backwards, we have to truncate this. We have to cut the graph. So we actually cut this one like this. Cut off this piece, and we cut everything to the right of pi. And so if this is cosine of x, this is the graph we actually do the inverse on. So notice that this is 0 to pi, this is 1 to minus 1. So y equals inverse cosine of x looks like this. From 0 to pi becomes my new output range, and from -1 to 1 is my input. I live in this little box, and I look like this. This would be pi over 2 right here. Those are the only two I'm going to talk about. Oh shit, one more. Just one more. This is probably the most important one of all. For inverse tangent, so if we just have tangent of x, that looks like this. It's got asymptotes, and pi over 2 minus pi over 2, and then it repeats over and over. We actually just take this middle chunk, and we cut off all this stuff, and take this and flip it over y equals x. So when we have inverse tangent, in other words arctan, it's going to look like this. And this is cool. Pi over 2, negative pi over 2, we've got horizontal asymptotes. So that's inverse tangent. That's probably the most important. Good Lord. Oh, we're doing all right. Okay. That looks like a lot of stuff. That's the quick review of inverse trig functions. If you would like a more in-depth one, shoot me an email. I will hook you up with videos to help you understand this stuff. Because now, this isn't even calculus, right? This is pre-calc. We haven't done any calculus. Now I want to do some calculus. Let's find formulas for the derivative of arcsine, derivative of arctangent, and arccosine. And these just mean, this is just inverse sine, inverse cosine, or inverse tangent. So I'm just using both the notations. You know what? I'm just going to give them to you now. I feel like there's been a lot of derivation today, and I understand you have a finite capacity for that. Just like the sheer will to care, even if you're following, to care for as long as I'm asking is a lot. So I'm going to give these now, and then I'm going to derive one of them at the start of class on Wednesday. So here's the laws. The derivative, here's the easy one. Derivative of arctangent of x is 1 over 1 plus x squared. We can ask a friend in class about that. We could also, I bet, ask that same person about these formulas, but we won't. And then God help us, there are 3 co-function inverse derivatives. And they're just fucking horrible. They really are. I don't even, like off the top of my head, I haven't reviewed them in a while, and they're so seldom used that they don't matter a lot. And I don't think we're going to look at them right now, because I just want to do this stuff. There's enough here to learn from. So, friends, can you find, using the chain rule, these are all chain rule problems, and you're going to need these laws. So right now, what I'm asking you to do is take a law you've just been given, use it to extend to a chain rule case. Here's the game. This is all the game you're going to need to know, besides all the other games you've already learned. So the chain rule, use the chain rule. What is the derivative, let's start off low, of inverse tangent of 3x. Just chill. Here's the laws. See what you can come up with. All effort is good. Kind of nice to get through all that stuff too. It's heavy. I will write out special chain rule versions of these for you. Just in case. This is beautiful. Just be careful down here when you remove those parens, because that would be a nightmare. Just a small thing. I see you've got the game. Do I have enough light here? Is this okay? I like it. This is my kind of light. That should be okay. It's okay. Okay, sorry. Yeah, no pressure. No pressure. How are we doing now?
I'm not sure if I should just insert the X or click on the first one so for like tangent. I don't know if I should just go like this.
Yeah, keep doing it. There you go. Perfect. Okay, put that all in the box so there's parentheses around the 3x. No, just like, yeah, like that. Perfect. Okay. Yep. And then, okay. Now you, so that would be 3x. Okay, is that a 3x you were?
Yeah.
Wow. Okay.
That's not even that small.
It's, well, you're not 55. So, I don't know. With double vision, for God's sake. Poor me. How's it going, Joey? That's good. That's looking good. Yeah. Indeed, and even expands. Of course. So that's looking good. Times the derivative of the 3x. For the inside. Chain rule, you just did the outside. You look it up. Okay, cool. Okay. Looking good. Okay. Yep. Were you about to do what I was saying? What I was about to say? Just parentheses around the 3x. The whole thing is squared. That's it. Beautiful. Beautiful. Yeah. All right. These rules are your friends, right? And Alex said, do I just put the thing in the box? Yeah, you just put the thing in the box. There's still work for you to do, but 3x is in there. And you might want to, if you are a person who habitually abuses parentheses, you should put parentheses around that box squared, because everything that's in there is going to get squared. So this guy is going to be 1 over 1 plus 3x quantity squared times the derivative of 3x. And that's a 3. And this is just simplifies into something quite beautiful like that. How about this one? Please find, every once in a while, a math teacher realizes, you know, there are other variables besides x. This is one of those moments. Some chain rule. And I'll put one more over here. That's that. Run to the restroom, right back to. I'm gonna talk this one through while I'm doing it. Chain rule, I know it's chain rule because when I read it, I say cosine of arctangent of y. That word of indicates composition. If you don't know what composition is, you might not say it that way, but you need to get in the habit of it. So the derivative of cosine is negative sine. So I do the outside first, leave the inside alone, times the derivative of the inside. That's a formula that I literally copied down. So that's just inverse tangent derivative. So this is negative sine arctan y times 1 over 1 plus y squared. And that's it. You could group those together if you want. You could put this underneath. Your choice. Let's come over here. Again, natural log of. And I want to use our chain rule version of natural log. I highly recommend on a sheet you use these chain rule versions. These are the ones you have ready because they're the ones that are going to be the most applicable. This even works if there's a freaking x inside there. So it's the derivative of the stuff over the stuff. So this is going to be derivative of the stuff. I think that's a Greek eta. I wasn't sure. I knew it's pretty. And it's a valid symbol. Works. So that's step one, just using that. Step two is, I got a formula. Derivative of that is -1 over over square root 1 minus eta squared over arc cos omega. And, you know, if you want, I would do this. It's not, this isn't incorrect at all. It's just that's prettier. Less fractions is always better. Any questions, friends, on this? I think we just need some practice. Let's call it for today. That's enough. That was a heavy day. There's a lot of shit that went down today. And keep an eye on your email. If you came in a little late, I'd said that Wednesday we're expecting a lot of snow. If there's a lot of snow, we're going to be online. So keep an eye on. I'll email you in the morning as early as possible on Wednesday. Yeah. Say that again? I'm sorry. Did I not do that? I did do that. I did do that. Yeah, it's just written out a little bit differently. So, so do you agree with this? It's okay. It's all good. It's all good. Let's talk. It's all right.
Wait, so one,
So here's this.
oh,
So I did it.
I see what you're doing now, okay.
You good?
Yeah, and then you, multiply it by,
Find the derivative.
oh, by the derivative.
But I kind of just put it on top, so I think that's where the two of us just differ. You're right. This is so what you do. Thank you. Bye-bye. But you're using the arctangent derivative. So that's arctangent.
Okay,
And that's
so then, so you multiply it by, how would it end up on top?
Okay, so let's go backwards. So this is. And then this is this.
My mom works at a giant consulting firm, so
Yeah.
anything
Yeah.
stock related, she just gets.
Multiply, I mean, this is just literally, I could make this a fraction over 1.
Oh.
And I just brought it across, right?
Oh,
Like
okay.
if I had a third times 2, you would totally agree that that is the same thing.
I see what you're saying.
Good, awesome, thanks.
All
Woohoo!
right.
Nina had a question, that's great.
I was just, yeah.
Holy shit.
Well,
I'm
she
like
got a question,
so
we're
tired,
all
though.
fucked. I mean, I should probably.
Yeah.